Next, exercise 10. So here we are given 3 rotations R1, R2 and R3 and 3 reflections F1, F2 and F3 in the dihedral group, which is the group of symmetries of a regular n-sided polygon. We have to figure out what this element is, whether it's a rotation or a reflection. We know that this is again an element in Dn because Dn is closed under the formation of such a product, and we also know that in Dn every element is either a rotation or a reflection. So this is either going to be a rotation or a reflection. We have to figure that out. So we can use the previous exercises that we saw. There we saw that the effect of applying 2 rotations is the same as a single rotation, and a rotation followed by a reflection or a reflection followed by a rotation, since it changes the orientation of the polygon, so it has to be a reflection. And finally, if you take 2 reflections, then that is equivalent to a rotation because we get the original orientation back. So we have to figure out according to that, since R1, R2 is a rotation, R1 and R2 are 2 rotations, so their composition is also a rotation. So that's why R1, R2, F1 must be a reflection. Okay. R3, F2 is a rotation and a reflection. So since here the orientation has changed, I mean this operation changes the orientation of the polygon, so it can only be a reflection. This is a reflection and so is F3, R3 because of that same reason. Thus, R1, R2, F1 is a reflection, and what shall we get when we consider these 2 reflections side by side, I mean together? Their composition, since both of them are reflections, their composition will be a rotation. And R3, so this is the composition, R3, F2, F3, R3 is a rotation. That means we have a reflection, this part, this much, and followed by a rotation. So their product must be a reflection ultimately. Hence, R1, R2, F1, R3, F2, F3, R3 is a reflection. So that is the solution. Then we see exercise 11. find elements A, B and C in D4 such that AB is equal to BC, not AB equal to AC. Okay, that I made that mistake while taking this question down, but A is not equal to C. So this is not cancellation. I mean, if we had A equal to C, we would not call it cancellation but rather cross cancellation, because there B is not on the same side of the product on both the sides. Thus, cross cancellation is not valid. And the answer or the solution is just this. I mean, you can find other examples of A, B and C, but I found this one. Note that R90 composition H is equal to D prime is equal to H composition R270. If you go to the symmetries in D4, that is the symmetries of a square, which is there in the text, there you will see what these symbols mean and what symmetries they are, and looking at that I mean, looking at them, you will be able to see that this is, both of these products are equal to D prime, which I think is a reflection about a diagonal as the axis of reflection. But clearly the rotations R90 and R270 are not the same thing. So that's just it. Then exercise 12. Explain what the following diagram proves about the group Dn. So here something is given. I think I should use a ruler to draw it. I can do a freehand drawing also, but it won't look nice. Just like that, below this we again have transformations. Okay, so this, let me just first write everything and then we will discuss about it. 2. So here the transformation is f, it's being called f 1 to n. Here this is r 360 divided by n, 1 n minus 1, and then below this we have 1, again same thing, 1, 2 and n. Okay, so we have been asked to explain what this diagram says about the group Dn. So what the diagram really says is that Dn is non-abelian. And why is that so? Note that these are actually portions of a regular insided polygon which shows 3 vertices and I should not say vertices. Should I say vertices? In plane geometry also we have vertex and edges. Okay, so which show 3 vertices, each one of them shows 3 vertices and 2 edges which are adjacent in the polygon. For example, if you have a regular, this is not regular but just consider it a regular hexagon, then you have, for example, these 2 edges. If you are naming the hexagon like this, then you have this portion, say, where these vertices are 1 and 2 and this is your n, 6. If you are considering this, then you are considering d6. So what f does is that f flips the figure about this axis, okay, which is bisecting this angle. That gives us a symmetry of Dn. So 1 stays here, 1 is unchanged because 1 lies on the axis of reflection. 2 and n are interchanged. After that, we perform a rotation in the counterclockwise direction through an angle 360 divided by n. So that will bring n to the position of 1, 1 to the position of 2, and it will bring n minus 1 to this position. So that's why we have this. So this means applying f first and then applying this one. Okay, that is according to the convention for composition of function, the first row shows us the consequence of the composition on this part of the regular regular insided polygon, this composition. First we apply f and after that we apply this rotation. So a reflection followed by a rotation. In the second row we are doing the opposite, that is we change the order. Here we first apply the rotation and then the reflection. So if we rotate it like this, about the center of rotation through this angle in the counterclockwise direction, then 2 will come here, 1 will come here, and okay, what is have I, oh, this is not n, this is 3. Okay, so I wrongly wrote it as n. So 3 is here somewhere, the vertex that is adjacent to 2. So 3 will take the place of 2, 2 will take the place of 1, and 1 will take the place of n. And then we do the vertical flip, vertical reflection about that vertical axis. So 1 and 3 are interchanged. So you can see that these two compositions do not give us the same thing. That is, all the vertices have, I mean at least these 3 vertices have changed positions, that we can clearly see here. So that's why these two are not equal, and as a result the group Dn is non-abelian. So you can just simply, I mean, argue like this in your mind, and you can write the final conclusion, because we haven't been asked to, we have been actually asked to explain what the following diagram proves about the group. So the explanation, if you want to make this solution somewhat longer and somewhat more elaborate, you can write the above diagram shows this, and hence the group Dn is not abelian. Okay, so that will be the solution. Okay, now we have come to again the question of determining the group of symmetries of some other figures which are not necessarily inside a regular polygons. That regularity is now not there. So let us see. Describe the symmetries of a non-square rectangle. So this is exercise 13. Construct the corresponding Cayley table. A non-square rectangle. So let me just draw the figures, and then we will see why they are the only symmetries. I could have drawn the rectangles of the same. You can understand they represent the same rectangle in a different arrangement. Even if really in this picture they are not of the same size. I mean, this seems a bit longer, but it will be okay for our purposes. Can we draw two more here itself? Yes. And one more operation. Okay, now let's name the vertices A, B, C, D. So the first operation is R naught, which you by now know is a rotation through an angle 0 degree in the counterclockwise direction. So it does not change anything. A, B, C, D. Then A, B, C, D, and the next one is R 180. So it changes, it rotates in the counterclockwise direction through an angle 180 degree. Doing that, we will have this A, B, C, D. So this is one symmetry, this is another, and then A, B, C, D. Okay, so this is V. That means here we are going to do a vertical reflection about the perpendicular bisector of these two sides, BC and AD, the two horizontal sides. So we will reflect like this. So that will give us AB, D, C. And then there is this C1. C1 is achieved by performing an R180 rotation to this arrangement. So that does what? It first takes A to the place of D. Actually does not take A to the place of D, because if you perform one 90-degree rotation, it comes in this upright position, and then you perform one more 90-degree rotation. So A will be here, A, and then, but we have to be careful. If we are following, okay, you see, because of the flip, the orientation has changed. Now it is clockwise, A, B, C, D. So one rotation will not change the orientation. Now, I mean, after this, the new orientation will be maintained by this rotation. So we will continue to have A, B, C, D in the clockwise direction. I hope that's what I have got. A, B, C, D, yes. Okay. Now there may be some questions in your mind, like Are these the only symmetries? Let us see. So I have started like that. No, so here you can see, just like that triangle, I have made a non-square rectangle cutout here. This time I have made it big because my mother said that the triangle was too small, and I think you also felt that, and I also felt that, but you didn't say anything. So this time I think it's better to make out. You can make out the vertices A, B, C, D. So there we have ABCD. So the first one is clearly, I mean, it's nothing. It's the identity. It does not do anything. For the second one, we have ABCD. So if we change the, I mean, if we rotate it counterclockwise by 90 degree through an angle 90 degree, then we come to this position. And then one more 90 degree rotation gives us this. So A, B, C, D. A, B, C, D. So that is the thing. And now we are going to change the orientation by that vertical flip. I mean, flipping about a vertical axis. So we flip like this and we come to this arrangement where these are the, I mean, we are maintaining the same vertices on both sides. Here we have A, so on this side also we have A. We are maintaining the positions B, B, C, C and D, D. Okay, so we have got this. That means if you look from here, A, B, C, D, A, B, C, D, and after that if we rotate again by an angle 180 degree in the counterclockwise direction, then 90 degree, 90 degree. So A, B, C, D, A, B, C, D, that is fine. But what about maybe some other operations? You can see one thing, that unlike a square, since this is a non-square rectangle, rotation through an angle 90 degree does not give us the same position. I mean, it's now upright, it's not horizontal like this. These rectangles, if we rub everything of all the levels, these rectangles are identical. So that's why these operations are symmetries. But a 90 degree rotation is not a symmetry this time, which it was in case of a square. Okay, so R90 is not a symmetry of this rectangle, and because of that R270 is also not a symmetry. Now we come to the reflections. We have already carried out one reflection. I mean, from here we have done this, and then we have performed a rotation. But by now we already know well that a reflection followed by a rotation can be achieved by a single reflection. Now, can we really do that? I mean, you see, you have this one and you have to reflect. Okay, so so instead of a vertical axis, now we can use the horizontal axis, that is the perpendicular bisector of the sides AB and CD. Okay, if we do that, if we reflect like this, then we have ABCD, ABCD. So this operation can be achieved not just like this, but through a horizontal flip too. So that means a horizontal flip through this axis does not give you anything new. That is the point. We get this itself. What else are there? You can see that we have drawn diagonals, the two diagonals. If we reflect about the diagonal, then what happens? You see, B and D B and D suppose I am reflecting about this diagonal, then B and D stay in their positions and A and C are interchanged. So do we have that? But okay, I have a doubt. If we are okay. So what really happens when we reflect about this diagonal? Let me put it like this and keep it as horizontal as possible and then do the reflection. I mean, it's better to keep it like this, and then if I reflect about, say, this diagonal, like this, if I am doing, then am I getting this clearly? I mean, my doubt is this: if I am reflecting about this axis, oh, I can rotate the pen itself, no? Oh, then I don't have this flat position, I end up with something else. That is, I am reflecting like this, and you see this axis continues to be in the same position as this diagonal, the diagonal of this, but now it's neither horizontal nor vertical, it's somewhat slanted, so we don't get that same thing back. Okay, the same is true if you reflect about this axis, so that's why we were not getting that horizontal position like this. It's difficult to maintain a constant line in space, but you end up with something like this. You can do it yourself and convince yourself that these diagonals are actually not axes of symmetry. They were axes of symmetry in case of a square, but for a non-square rectangle, unlike the perpendicular bisectors, these are not axes of symmetry. So that's why we don't get anything new if we perform. I mean, we have seen all the possibilities. Now we are going to construct the Cayley table. So here we have 4 elements. So that means I will need 5 rows and 5 columns. One, 2, 3, 4, 5, and then 5 columns. 1, 2. Okay, and the table ends up being like this: R0, R180, then V and C1. Here in place of C1 you can also write H, which will represent a horizontal flip. So these rows and columns are just the symmetries or transformations themselves, because we are composing with the identity transformation R0. V and C1, and then we have this. Here the leading diagonal positions are all R0, and here we have C1V, R180, C1V, R180. Okay. Now before verifying that this table is correct, you can just see one thing which we have already discussed before, that in any such Cayley table, each row and each column, I mean this part, okay, leaving the outermost rows and columns on this side because they contain the just the elements which we are composing. Actual table is, which shows the composition part, is this much. In that part, every element appears in each row and each column exactly once. R0 appears in the first row, first column, second row, second column, third row, third column, fourth row, fourth column. R180 appears in the first row only once, in the second row only once here, in the third row only once here, and in the fourth row there. What about V? V appears here, and then in the second row it appears here, in the third row it appears here, and in the fourth row it appears here. So in every row there is exactly one V, and consequently in the columns also the same thing is true. And finally C1 occupies these positions. Okay, so that thing is, there is no problem with that. Now you can verify, say let us verify that V180 is okay, V180, R180 is C1. In fact, that's how we perform the operation, so there is no need to verify this one. However, shall we get the same thing C1 if we perform R180 first and then on that we perform V? Let us see. So where is the rectangle? So this is the initial position. If we perform R180 first, then this is our position, and then on that we do a vertical flip. So we end up having A, B, C, D starting from here and moving in the clockwise direction. So we are, this table suggests that that is C1. So yes, A, B, C, D, A, B, C, D. So this is correct. Just like that you can verify the other entries also. I am not writing anything else here, so you can see that. I mean, if you want, you can write these explanations. In fact, you should write to complete the solution what R0 actually means, what R180 actually means. You have to describe those things. See? Describe the symmetries. Then we come to the other types of quadrilaterals, that is where the internal angles are not 90 degrees. So this is exercise 14. Describe the symmetries of a parallelogram that is neither a rectangle nor a rhombus. Okay. That is neither a rectangle nor a rhombus. Okay, so that will actually be obtained by applying a shear force to this rectangle to bend its sides, so that you get a parallelogram. And I have a parallelogram here, but before that let us just draw the pictures and then we will see. So here we don't have to form any Cayley table, we just need to show the symmetries. Let me make this side a bit longer. How did I name this? Oh, here however I have started from this vertex. Doesn't matter, you can name any one of them A, B, C, D, or any name in fact you can give them. So the first transformation of course is R naught, which is the identity, it does nothing. And then only one more transformation. Okay. So A, B, C, D are 180. A, B, C, D, and this is R 180, rotating through an angle R 180. We need to see that this really brings the parallelogram to this position. However, after performing that operation, we end up having this. Wait, I think I wrote it incorrectly. Let me just see the cutout and then it will be clear. So here we have a rectangle, a parallelogram that is neither a rectangle nor a rhombus. And oh, did I okay. No, so here the cutout, I have labeled the cutout according to how I originally named the rectangle itself. So it starts from here, A, B, C, D. I have to maintain that, otherwise this demonstration cannot be given. A, B, C, D. A, B, C, D. So now if I rotate it through an angle 180 degree, so this is 90 degree and this is another 90 degree. So yes, it comes back to a similar looking state, similar looking position. So I have A, B, C, D. A, B, C, D. Now what is the difficulty here in considering a reflection? There are several axes that we can try which are somewhat doubtful. Of course you are not going to reflect about this axis, or say for example this axis. They are already axes of asymmetry. They are not giving you the symmetrical position or the same position after the transformation is performed. So the thing is that if I have to verify whether these two diagonals are axes of symmetry and whether the bisectors, this time the bisectors are not perpendicular but nevertheless bisectors are there, whether they are axes of symmetry. Say I take the horizontal bisector. If I flip the figure like this, no, it becomes like this, not like this. So that is not an axis of symmetry. And because of that same reason, a bisector like this, if I flip the figure, oh, I am flipping about this bisector, so that means I should flip about this. Oh no, so it becomes even more asymmetric. Asymmetric in the sense that we don't get the same position back, similar looking position. So these bisectors are gone. Now what about the diagonals? If I flip about this diagonal, then it becomes upright like this. Okay, so that is not the thing that we want. And what about this diagonal? If we flip like this, then clearly it has not come in that same similar looking position. So that's why in this case the symmetries are even fewer than the rectangle. How many elements did D4 have? D4 has 8 elements, which is the group of symmetries of a square, which is a figure as symmetrical as you can get, having 4 vertices, and which is a convex polygon like that, 4 vertices and 4 sides. After that we have come to this group, which is the group of symmetries of a non-square rectangle. So here instead of 8 symmetries we have only 4 symmetries, R0, R180, V and C1. So the number of symmetries has been halved. Coming to a parallelogram that is neither a rectangle nor a rhombus, so that note that it's not a rhombus either, because all the sides are not of the same length, only opposite sides are of the same length and they are parallel. So here there are only 2 symmetries, so it is halved even more. Okay, 8, 4, 2. But now we are going to consider the symmetries of a rhombus. Because a rhombus is more symmetrical than such a parallelogram in the sense that at least 4 of its sides are equal, so that thing will be reflected by the size of the group of symmetries. Here the number will increase a little bit. It is not going to be exactly 2, it will be something more than 2. And these are the symmetries. So I have to draw a rhombus, okay, which may end up being not a rhombus. Okay, so let me tell you that in the beginning itself, because I am drawing without any measurement whatsoever. And I am trying to make it look like a rhombus as much as I can. So we have to adjust these sides. Okay, then like that. And 4 more like this. So let me try at once. You may object to this wastage of time. I mean, I can just simply draw them without using the ruler and show the symmetries, but these things look good. So it's, I mean, we are not in a hurry. We are not going to write. You may be, I mean, you may be in a preparation where you are going to write an exam, say, but I'm not in any such position, so I will do it in a relaxed manner. Okay, so here we have the vertices A, B, C, D. So the first operation is identity, it does nothing. The second one is this R180. Okay, despite having a little more symmetry than the parallelogram, so this is a rhombus, this is an accurate rhombus, okay. But 90-degree rotation is still not an option. Let's see what happens if we do a 90-degree rotation. It just becomes like this, okay. It comes in the upright position. It comes in the upright position, but the thing is that now the slant is there, that way, not this way. So R90 is not an option. R180, however, is an option, because I should grab it here, so that becomes the center of rotation. So this is 90 and this is 180. So I get A, B, C, D. Okay, so this is one symmetry, and then what did not work for us in the case of this parallelogram, that is the reflections about the diagonals, that will now work in this case. Let's see why. A, B, C, D. Say we want to reflect the cutout about this diagonal, so we can call it D1, and there is the other one D2 about the other diagonal. Then are we really getting a symmetry? So it will be like this. So A and C are interchanged, B and D Yeah, that's the way to flip it. So here you can see that again we get that same slant, so it comes back to the similar looking position. So here B and D are interchanged, they stay the same, and A and C are interchanged, and lastly we have the flip about the other diagonal. So here A and C will remain fixed and B and D will interchange. So you can see that in these transformations the orientation is in the counterclockwise direction, A, B, C, D, A, B, C, D. However, once we perform a reflection, the orientation changes. Now it's clockwise, A, B, C, D, A, B, C, D. Okay, so here again we have got 4 more things. However, the flips about a horizontal axis, about axis parallel to the sides, are still not an option. If you flip about a horizontal axis, then you get like this type of slant this way, so that's not a symmetry. And if you flip like this, again you get a that way slant, so that is also not a symmetry. So these are the symmetries of these figures, of a rhombus which is not a square, and of a parallelogram which is neither a rectangle nor a rhombus, along with a rectangle. Okay, now after these things are taken up a notch by considering conic sections, ellipses, hyperbolas, those things. Describe the symmetries of a non-circular ellipse. Do the same for a hyperbola. Okay, this time I cannot use any ruler or anything. I can use ruler to draw the axis, but not the ellipses themselves. So here we have to identify points. Okay, this is going to be as bad. I'm trying to make it as good as possible, but you can already see that it's tilted this way. So these are the major axes, and non-circular we have been restricted to consider a non-circular ellipse. I need some ink. So we will use these axes to identify points. I mean, we are going to identify extremities of these axes and try to see how they are transformed by a transformation or by a symmetry. So we are going to name these extremities like this. So A, B, C, D. So the first transformation is just R0, which does nothing, and then the ink will take some time to come. A, B, C, D. Now if you want, you can think of rotating this. Again, note that the situation is somewhat like the rectangle, although this is clearly not a rectangle, it's a conic section, but as far as these things are concerned, or as far as the general shape of the thing is concerned, you may think of this as obtained from a rectangle by beating it up severely, damaging its corners and giving it a look like this. Or for example, if you leave a rectangular stone, okay, and it in the elements outside, it is after some months it will take the approximately a shape like an ellipsoid. That's how pebbles are formed near rivers. Okay, so like that you can think of the situation. So R90 is still not an option, R180 is an option, so those things are there. However, this time instead of thinking of the rotations, let's try to think of reflections. You can, but rotation also we have to think, no, because if we reflect, we will get something else entirely. Reflection will change the orientation and rotation will not change the orientation. Okay, so we have to consider reflections. I don't know what I was thinking. Okay, so this is say R180. So if we do R180, A will first come here and then A will come here. So A, B, C, D. So this is another symmetry. Like that, two more. now we have to flip, and we can flip either with respect to this axis or this axis, and we are going to do both of them, of course. So say we flip with respect to the minor axis, the vertical axis, then these two will remain unchanged and A and C will interchange their position. So now the orientation has changed. Instead of the counterclockwise sense of rotation, we now have clockwise sense. And if we perform a horizontal flip about the major axis, then B and D will interchange their positions, A and C will remain unchanged. Note that this same thing is obtained from here by rotating this through an angle 180 degree in the counterclockwise direction. So these are all the symmetries. Are these really all the symmetries? Let me just, if we I believe these are all the symmetries, but do we have any other axis of symmetry? That's what I am thinking. Any other axis? No, if I take another axis, that is what I am trying to think here is a situation like the diagonal of a rectangle, something like this. But how will you describe that axis? In any case, that axis will not be an axis of symmetry. Just like in a rectangle, the diagonals are not axis of symmetry. So here also you can pretty much understand any such axis whose definition is also somewhat difficult. I mean, you can think of such an axis like this. You can think of a rectangle in which the ellipse is inscribed, so that all the sides of the rectangle are tangents to the ellipse at these extremities of the major and minor axis. That rectangle will have diagonals, flipping or reflection with those diagonals as axis of reflection. Now that will also not give us anything, because after all we will have a rectangle, and if that was the case, if that gave us an axis of symmetry for the ellipse, then that also would have given us an axis of symmetry for the rectangle, that is the circumscribing rectangle. Now, so there is, according to my logic or my analysis, there is no other symmetry that an ellipse has. So we have 4 symmetries. How many did a rectangle have? See, rectangle also had 4 symmetries. Okay, now what is the condition? What is the situation with a hyperbola? A hyperbola has 2 disconnected components, two connected components which are disconnected. Now, what points will you consider for a hyperbola? That is one question. You can always draw 2 axes like this, no matter how the hyperbola is drawn. Okay. So for the hyperbola, you can do this. I almost forgot the things. There is, oh, there is a focus, no? Ellipses also have focus, but in this case we need the focus, the foci. So you draw these two perpendicular lines passing through the foci, and here the drawing is not okay. I mean, the two lobes are not symmetrical, so that's why it's becoming like this. However, they will form a rectangle, and you can use this rectangle to gauge the symmetries of a hyperbola. So according to me, there will be 4 symmetries. Just like a rectangle has 4 symmetries, this one also will have 4 symmetries. One of them will be, of course, identity. The other will be achieved by performing a 180-degree rotation. Note that R90 here also is not an option, because if you do an R90 rotation, the hyperbola will look like this. But that clearly is not, they don't look alike. So you have to do one more 90-degree rotation. So that will bring you the same position back. Okay, so R180 is 1, R0 is 1. Then you can flip, about the horizontal axis, so that AB will come here and CD will come here, and about the vertical axis, so that AD will come there and BC will come there. Both these flips will change the orientation of these vertices. I think these are the only 4 symmetries of a hyperbola. If you find any extra symmetry in these solutions, then please let me know in the comment section below. After this exercise, there is one more that tells us to find the symmetries of equally spaced edges, infinitely many edges like this, okay, which are equally spaced and which continue in either direction without any end. So this is an infinite string. In this case, the group of symmetries will be infinite. There will be infinitely many symmetries. Do you know why? You see, besides that rotation, reflection, all those things, I mean, this is just like a rectangle, no? So this will give you 4 symmetries. But besides those things, you have translation symmetry also. Since these things are identical and equally spaced, what you can do is translate the figure by 1 unit, by that separation, either towards the right or towards the left. That will again give you an identical position of this infinite strip of edges, and that translation will generate an infinite group, because you can translate by 1 unit or by 2 units or by 3 units, in fact any natural number units or any negative integer unit. That is, you can translate on to that side also. And when you combine these translations with the rotation or the reflections that you get, then you will get all the symmetries. And note that when you reflect one of the figures, then the entire figure gets reflected. Okay, so you can either perform this reflection or you can perform this type of reflections also, horizontal reflection, either about this axis or about this axis. So there are many symmetries, and in the next video we are going to look at all such symmetries. It may seem like these solutions are speculative. They are not final in the sense that I am not really sure that we have all the symmetries. The thing is that I may have missed something, so you should keenly look at the thing, look at the solutions and see whether I have missed something. If that is the case, then just let me know. So with that, I end this video here. So we will see more in the next video. In fact, some exercises that are going to come involve some quite intricate objects like snowflakes or things that I will somehow show, okay, and we will try to find their symmetry groups. Okay, so with this I sign off for tonight. This is me, Lucifer, from a mathematical room. If you are new here, please subscribe to my channel, and that's it. So have a nice night.